Imagine freezing an electron. What is an electron? A building block of the atom, which in turn is actually a building block of everything around us. Essentially, we're looking at a mere component of an atom in space, and we want to freeze this electron within the space and then use this space to count how many electrons can cycle through within a given time. What would it take to freeze such an electron with its high energy? What would it take to count the electrons that are transported through that space? Good day, I'm Dr. Nashita Anif, an electron microscopy specialist within the EBE faculty at UCT and a graduate in solid-state physics. My background focuses on building semiconducting nanostructured devices using electron beam lithography, and this talk focuses on the technology used in this exciting semiconductor research wherein these devices can trap an electron within a quantum dot. What is a quantum dot? A zero-dimensional space. And this technology is in the race to find a standard for current and complete the quantum metrological triangle. The quantum metrological triangle is the voltage, resistance, and current components that are related by Ohm's law. It uses the Josephson voltage standard, the quantum Hall resistance standard, and the standard for current. The magnitudes of these standards have been determined by quantum phenomena that rely on the fundamental constants of nature. These are now widely accepted by the revised SI system of units. The definition of the ampere, however, the electrical base unit of current, and the standard for current is an ongoing investigation, as this has not been determined through quantum characteristics using these fundamental constants. Now, within the semiconductor research industry, high levels of accuracy for measuring current in single electron transport measurements are underway in order to close the gap for the standard of current. Now, one such way is by means of evaluating single electron pumps, also commonly known as quantum electron pumps at high frequencies, and this is within the gigahertz range. The quantum metrological triangle is also used as a test method to check the consistency of these quantum effects and to close the metrological triangle by determining a current standard with high accuracy. A quantum electron pump can be described as a nanostructured device that electronically enables single electrons to be confined to a zero-dimensional space, essentially a quantum dot, and to transfer these electrons across the oscillating gate barriers, which ultimately generates a current at high frequencies. So, to measure this, we will investigate quantum electron pumping devices that portray single electron transport effects and can contribute to high frequencies with high accuracy at ultra-low temperatures. We have to think of quantum dots as this gated device which is confined to the quantum electron pump. In these pumps, electrons are collected from the source as the entrance barrier is lowered such that the electron is captured within this quantum space of discrete proportion. It is then confined at this point in zero dimensions and cannot move. As the entrance barrier is then increased, the trapped electron is then able to exit at the opposite end and thus successfully transferring a single electron across this gated barrier pump. This is the ultimate transport of electrons across a quantum dot. The number of electrons transported through the quantum dot generates a current with high-level frequencies, which can be attributed to the current standard. The ongoing pursuit lies within the need to increase the accuracy of the generated current by producing low-level currents within the nanoamp range at high frequencies within the gigahertz range. In order to attain single electron transport within a device, we have to produce structures within the quantum regime to fulfill the characteristics of electron transport, measuring the current produced and capturing these measurements for analysis. To introduce quantum effects into a material, we have to reduce the dimensionality from a bulk sample in 3D, which shows classical effects, to 2D, 2 dimensions, and furthermore to one-dimensional quantum wires and zero-dimensional quantum dots. This reduced dimensionality of an electron pumping device is a semiconducting nanostructure confined into a quantum dot with narrowly etched oscillating gate barriers fabricated on the surface. In order to create these quantum electron pumping devices, we use a microfabrication technique that is available at the electron microscope unit at UCT. The fabrication technique is electron beam lithography. It forms part of the advanced scanning electron microscopy techniques wherein the beam scans the resist-covered sample according to a pattern generator. To fabricate the devices, we locate the microstructure, the nanostructure, on the surface of the semiconductor substrate and pattern the gate barriers to confine the space for electrons to be transported. The resultant devices are coated with gold to form the gate barriers across the nanostructured semiconductor. Once complete, the devices can be transferred to a dilution refrigeration unit. This unit allows for the device to be exposed to ultra-low temperatures within the millikelvin range. Just think about a fraction of minus 273 degrees Celsius. Very, very low freezing temperatures. So this allows for the confinement of electrons and quantized charged effects to occur. The capture of electrons within the quantum dot and the transfer of electrons through the quantum dot can be measured. The generated pumped current during the electron transfer yields characteristic pump maps which can be affected by varying parameters such as temperature and magnetic field. We continue to investigate these devices for high-level accuracy at these different parameters. In studying the single electron transport within semiconductor nanostructured devices, we contribute to the research for producing a current standard by testing the high-level accuracy of these devices within the quantum regime. The race for the standard of current is thus ongoing. Where will we fare?